Think about a big old oak tree that's sitting in the middle of a field. That tree has been there for 100 years, and it has gone through droughts and rain and snow and cold and heat, and it is adjusting constantly to that environment. So it makes those adjustments biochemically in their leaves. You know, it's really easy to think of plants as being like almost inert. I mean, they just sort of sit there. But the fact is that these plants are constantly making adjustments.
What you're looking at are leaves all over the globe changing color for 1 full year. This is the first time we've been able to see vegetation from space in 3 plant pigments all at once.
For decades, we've been able to look at measurements of chlorophyll, the green pigment in plants that we're all familiar with. But it's looking at all the plants as kind of one whole because most all of them have chlorophyll. With PACE, we can see more colors. More colors means being able to sense more pigments.
Pigments are substances that absorb and reflect light and aid in photosynthesis. Now, in addition to detecting chlorophyll, PACE can detect other leaf pigments as well, like carotenoids and anthocyanins. Carotenoids are pigments that give us the reds, oranges, and yellows. They're always present in leaves, but they really show up when chlorophyll breaks down. Anthocyanins are the reds and purples that appear due to temperature stress and bright light conditions.
The leaves are designed to be solar panels, and they absorb a lot of light. But the problem that they have is if they don't have the nutrients or the water available to them to be able to photosynthesize successfully, the fact that they're absorbing sunlight could actually damage them. And so they have these other pigments that they use to help mitigate that damage and protect the leaves. These pigments then are signals to us that the leaves are stressed in one way or another.
We can start to see these kinds of signals all over the globe, potentially pointing scientists to areas for further investigation. The data allows us to see large-scale farmland behaving differently than the surrounding landscape. Here, in the US Midwest, the blues indicate relatively high carotenoids, suggesting stress responses of corn to a heat wave in August 2024. In Siberia, one of the coldest places on Earth, we can see larches, deciduous conifers, adapt to survive the long, cold winter. As autumn approaches, chlorophyll disappears in larches as carotenoids increase, seen in the shades of blue, and eventually lose their needles altogether. In the South American Pantanal, we see a region very different from the year-round green Amazon. The Pantanal is the world's largest tropical wetland and largest flooded grassland, and its seasonality is largely driven by precipitation patterns. The dry season shows us a shift from greens to reds as chlorophyll is lost. The greens return with the wet season in September. PACE continues to collect data on how plant pigments shift, providing an opportunity for researchers to study land changes in a new way.
The kind of people that would use this would be foresters to look at forested areas that are perhaps being affected by insect damage or drought stress.
We will be able to look at how the plants, how the vegetation changes after large disasters like really large fires or perhaps a large storm event.
These responses that the plants are making come in early. And so we'll be able to see them before you actually start to see leaves drop off and things like that.